Swayam Prabha. Digital India. Educated India.
Now, I hope you can see this whiteboard. Now, this chapter is basically called rock failure criteria. Rock or rock mass failure criteria. Okay. Now, so far, we have discussed only in the elastic zone. If you can realize, right from the beginning, we have not gone to the zone of stress strain curve. This side, we have not talked much, other than that plasticity thing, what we have talked. So this side, we have not talked much. We are mostly concentrated everything here, even in the stresses in underground opening. We are saying when the material is in this zone, that means it is not failing. Okay. Now we want to talk a little bit about this point first. What happened to that point where it starts to fail, or this is another word called yield. Okay, either rock yielding criteria or rock failure criteria. Sometimes they mean the same thing, and many times they are two different meaning. Okay, I think I one time told you that what is the difference between yield stress and ultimate stress. You see, it does like this. This is where it yield, and probably this is where it fail, and then it will come down. So this is that ultimate strength, which we call UCS, uniaxial compressive strength, and this is the yield stress, where a material depart from elasticity. My elasticity was like this, and it is clearly departing, but it is still increasing with the strain. The stress is still increasing with strain. Okay, this load bearing capacity is not zero. But for some material like brittle material, this will be immediately, it will collapse. So yield and failure zone, failure point may be the same. Okay. Now, what we are going to discuss now, how does this rock fail? If you would have been here, you would have tested the rock and many things would have been clear to you already. Okay, because in the lab you would have seen how the rock fails, but since you have not seen that in the lab, so it's a little bit difficult to visualize. But let me tell you how we do the test. Let's say I have a sample, cylindrical sample, and I told you if the D is, this is D, this will be at least 2.5 of D, this length. Okay. We sometimes accept 2 also, 2 times of D, but at least 2.5 to 3. This is what we say. Now, what do we do with this sample? We put it in the testing machine and we give a load here and we fix it here. That means the sample will be standing on a platform which is very rigid, and then from the top we are going to give the load. Now what we are expecting out of it, and sometimes we do triaxial also, so a horizontal pressure is given through oil pressure. Okay, it is all around. Mind that it is, since it's a cylindrical, it is, this pressure is given all around and they are same. So if we are not giving this confinement pressure, this is we call confinement. Okay, you may call confinement pressure also. So if you are not applying that confinement pressure, then it is becoming uniaxial. means my loading is only in one direction. Now, in this case, what you are seeing is we call it triaxial. And here I can say if this is my sigma 1, which is going to fail the rock, and if this is we call sigma 3, then a triaxial thing I call sigma 1 greater than sigma 2 equals to sigma 3. This is my sigma 2. So this is what is triaxial condition. So sigma 1 means my testing procedure is sigma 1 should be greater than sigma 2, which is equals to sigma 3, because two horizontal direction, this confinement stress are same. Now, in an underground or in an actual field, this is not the case. The actual case is sigma 1 greater than sigma 2 greater than sigma 3. This is the actual case, or we call polyaxial. This is polyaxial and this is called triaxial. Okay. And uniaxial, when this is equals to this equals to 0. This is uniaxial. Sigma 2 equals to sigma 3 equals to 0. Okay, we are not applying anything. That is called uniaxial. Triaxial, this is non-zero, and polyaxial is this. Okay, and this is the actual field condition. Okay, what we see in underground. So it's pretty difficult to measure this one. And as far as my knowledge goes, in India, there is only one machine which can test this. This is in IIT Roorkee. The machine is very expensive. Maybe some other institute now have purchased, but we do not have in IIT Kharagpur to measure this, where sigma 1 is greater than sigma 2 equals to sigma 3, at least for raw. Now, so we are confined. We have a very good machine for this, external machine, okay, where we can do this test. And you will be doing this test also when you come here. Okay. So under this condition, this we are expecting this sigma 1, which will cause the rock to fail. Okay. The sigma 1 will be okay. Now, if you remember, one time I told you about rock petrography. There, let's say this is a rock matrix I am trying to make. So there are some grains. These are, let's say, sand grains. And sand grains are diameter will be sub-millimetric to maybe 1 or 2 millimeter also. Okay, sometimes coarse sand is also about 3 millimeter. Have you taken sand in your hand anytime?
Yes, sir.
Have you seen what is the diameter of that sand? Next time you must observe these things. Okay, what is the diameter? Because this sand is giving us the strength, sand and that stone chips. So you have to see what is the size of that. You will see some diameter will be some 1 millimeter or sub 1 millimeter, somewhere in between 2-3 millimeter also. Now there are some small particle also sometime will be there in the rock, and they are silt. Silt is little smaller size. Now, do you know what is silt? Have you seen? SILT. So this is called silt. And this one is sand. Silt, you must have seen, gone to some riverside and you will see sometime in the side of the river, very fine whitish, sometime different color also. In the river bank, you will see those are theirs. A thick layer of that. And that is basically silt. And if you see the particle, it's very fine. It's even lower than the sand. Okay, if you take that thing in your hand, you will see it is very fine. So we are talking about this is sub millimeter. Maybe let's say starting from 0.01 or 0.001 millimeter to less than a 1 millimeter. Okay, it's very fine particles. So that can also be there. Then there is maybe another particle, and I am giving as like a dot. This may be there, this may not be there, and these are basically called clay particle. Okay, it's basically mud. You know the mud and mud particle. If you take it in your hand, you know this is very fine, just like powder. Okay, it's very fine. So mostly in the rock, these three types of particle will be there. Other than this, there will be something we call binder. If this is seen by in a very high resolution microscope. Okay. Now these are the binders. And let me write the name binders. Some people call cement. Okay. Some may call adhesive. Okay. So some kind of a adhesive type of binder, mostly with calcium oxide or magnesium oxide type of thing. You normally use adhesive, right? Like araldite or even what is that Febiquick. Next time you buy one, you see the composition of that. What is written there? What is made with that adhesive? You will see these two things will be there. They are very adhesive in nature. You know, the calcium is also in the tooth, right? And there are many other adhesive chemical, but these two are mainly present in rock. Sometimes ferrous type, ferrous oxide are also there. That is also a little bit adhesive, but ferric oxide is banned. So this adhesive material are there. Now what they do, they bind this particle to each other. And as you know, rock has formed billions of years ago, and it undergone many pressure, different pressure and temperature condition. And due to this condition, this binder really worked very well to bind this particle together. You know, how many types of coal are there? Can anybody tell me how many different type of coal? Just a general knowledge question.
I guess four.
Four. Okay, name one.
Peat.
First one.
Peat. Peat.
Peat. Okay. Okay, right. You are starting from the bottom one. Okay, peat. Then
Bituminous anthracite lignite.
bituminous anthracite lignite. Now, anthracite is the best quality coal. Okay, in India we hardly get. There are some in Raniganj area maybe. Bituminous is abundant in this country. Okay, even sub-bituminous. Our coal quality is not so good. Okay, and then There is another type is called lignite. Now this lignite is available in Gujarat, in Tamil Nadu, in some other parts also. Now this lignite coal, also called brown coal, okay, there is a reason for it, because uh, this is very young geology. You may say the coal has not formed yet, okay. If you would have given another 2-3 million years or maybe more, they would have formed actually bituminous, a very good quality coal. Now, if you go to those kind of mine, you will see on top of coal, in any other location, there will be sandstone rock. There is a sandstone. So sand has become stone by this binding effect. So they become a very hard rock. But if you go over there, on top of coal seam, there is still sand. They have not formed stone yet. Okay. So in some cases, a very weak material. This is very clear that the geology is very young, and all this kind of pressure and temperature variation has not gone through yet. And as a result, they have not become the solid rock which was supposed to. So this binder didn't get time to bind all these particles together. Okay, time or pressure or temperature, it didn't get. Now that is how is the difference. So it used to be sand and clay and silt and some binding material over there, and then they make this stone, sandstone, or same as shale. Shale is coming from that clay or mud with some sand in it. If you see, even there are some temples in our country which were built maybe 1,000 years ago. Now, do you think that time cement was there? The cement like we know today, we make buildings and all these things. Definitely 1,000 years ago, there was no cement. So how did they build those structure? When the some are pretty high, and they used what we know is, what it is.
Clay, sir, clay.
What is this local name? Calcium carbonate?
Limestone.
Have you applied? Huh?
Limestone.
Limestone. Okay. That means what? Limestone we call chuna patthar, right? So what is basically, you will see even these days they do not do, but in the previous days, if somebody got a broken hand or something, they used to put this tune, and then they used to bind that hand. But this has a binding effect, and you see the calcium oxide is over there. And if you see our this temple, those kind of thing, between two stones, if they are made with stones, if you observe very carefully next time you go, you will see this is present of this with some sand. So they used to mix sand and this, and then they put one after another, and then it works so beautifully. They stand more than 1,000 years, and not only in this country, in majority of the countries, the big structure are standing on like this. There was no iron rod in between. There's nothing. There's just big pieces of stone, and in between the stones they used to put this mixed with sand. Okay, so this technology they used to know, and the rock is also formed like this. So if this is the petrography of a rock, this is what is inside of a, if I do a very thin slice of the rock, if I find this, now you are asked to break this. Okay, that is what is the failure. You are going to now break it. So let's see how you can break this. Now I have a rock sample here which has all these particles and the binding things. Okay, it is made with this. I'm exaggerating the, and let's say I have binding things somewhere here in between all this. Now I am applying load, and I want to break it. Okay. So what will happen? Okay, this is what I'm trying to do. Now what will happen is, basically we put a steel platen on top of that. Same as here also, there is a steel platen and in between, and then we give load here. Basically this steel platen comes at a rate, at a particular rate. It comes down. We normally call it a strain rate. Let me tell you what it is. Strain rate means d epsilon by dt. Okay, we give a rate, and that's, let's say, 10 to the power minus 5 per second. Okay, this is what is the rate we are giving. Now, if this is the strain rate, and if this length is, let's say, about 100 mm, then what is the velocity? Can anybody tell me? What will be dv dt? Sorry, what will be v, which is du dt? This is the velocity. What will be du dt? D epsilon dt into L, right? Because this is nothing but del L by or U by L. Okay, if I do this is U by L multiply by L, so this will give me this du dt. You understand? This is nothing but Iscom-Legrand del epsilon by del T. Now this epsilon is nothing but U by L by del T. So I'm multiplying with L. So this is, sorry, it is del U. So this is giving me del U del T, which is basically V. Okay. So if I multiply this, what I will get? This velocity 10 to the power minus 5 into 100. So I'm getting 10 to the power minus 3 millimeter per second. So that means in 1 second, I'm coming down 10 to the power minus 3 millimeter. Now, if I run it for 10 minutes, let's say about 600 seconds, so I can multiply 10 to the power minus 3 into 600. This will be in 10 minutes. How much del U I will get? How much deformation I am expecting? So if you multiply, how much it got? 0.6 millimeter. So that means in 10 minutes, if this is the rate I am coming to 10 to the power minus 5 per second, my strain rate, if I move that platen, so within 10 minutes, I will come down, this platen will come down to 0.6 millimeter. So you can think of how small we are talking about. Okay, so we must have a very good measuring device, otherwise we will miss many data. Okay, and we have that machine which can measure this kind of displacement and this kind of thing. Now, when I'm coming at that rate or a velocity of 10 to the power minus 3 millimeter per second, if I'm coming down, what happens to, I delete this. Now, what happens to the particle right in contact, right here? What happens to this particle here? So this particle has to go somewhere, right? This will has to come down. But there are some particles, and this is completely fixed. You cannot move this. This is fixed. This is fixed. So this particle is trying to come down, and all these kind of binders are there here. So this will not allow you to come down. Okay. That means whatever the sigma I am applying, this must be able to do two work. One is to move these particles downward or sidewise. Okay. It may be normally the vector comes like that direction, because if this side is open uniaxial, then it will be coming the sidewise. And also this binder here, it has to break this binder. So sigma must do two things. One, it should move the particles, because the sand particle breaking is a very difficult task. So sand particle only will move. So move the particles. And number two, break the bond. So these bond between the particles. So sigma has to do these two things. Okay. Now when particle starts to move, what will happen? This particle, let's say I draw it a little bigger. Now you will understand. Let's say a particle is here and this particle is here. Now it has moved here and gradually it is now in contact with this. The moment it is in contact, okay, there is a normal force. Do you agree? The moment these two particles are in contact, there will be a normal force. And since there is a surface, they will generate a shear force. Okay, a normal force between two surfaces will always generate a frictional force. Okay, we normally call it shear. Ultimately, it will be shear. So there will be a friction, will be generating. There will be a friction. Now you think how many different ways this friction can be generating. This particle will be in contact with another particle, small particle, so many surfaces will be in contact. And each contact will have a normal force and a friction force. Okay. So move the particle meaning, this mean now it has to overcome this friction also. So friction must be overcome. So one is, that means it has to overcome the frictional force. Another is overcome the bond between the particle which has caused due to that adhesive or due to that calcium oxide or magnesium oxide or the binder. Okay. Now this continues as we are coming down, because the platen is gradually coming down. Okay. As it is coming down, this platen, these things are going on inside the sample. Okay, and you think how many different ways it can happen. Now, since rock is a natural product, okay, it's not a man-made product. Even the man-made product can also have flaws, have defects. Now, natural product definitely will have a defect. And we know that when you see a rock, you will see so many small cavities. It will have porosities. We have discussed that amply. So there will be some flaws somewhere here. Means, let me draw with some other color, also red color. Means this is a, there may be a opening like this. It is already inside. Okay. This has some water maybe, or may not be any water, just dry. But these are the flaws are already available. And the particles are all around this. Now, what happened? These flaws are then start to operate because they are already defect, they are already cavity, and when these stresses are coming, they will start to extend. Now, all of them will start to extend. Okay, means the small, big, whichever. Some may get closed, some may extend this flaw. Now, gradually, as platen is coming down, there will be a number of flaws which are maybe in the same direction, and that will become its weak path. Let's say in this case, this has become its weak path. Maybe there was another flaws like this. So this, it joins like that. So gradually, it forms a path. And this path, or the path of failure, or we call the shear path. So gradually, this will be its surface by which this is going to fail. And this is the, we call shear plane or shear path by which it will fail. Now it can be any direction. It may not be like that. It may be like this also. It may be like that also. It may be many. It may be multiple also. Okay, in some hard rock, we see a lot of multiple, this kind of path can happen. So ultimately, this is how rock get, failed. That is what is the petrographic analysis of failure of rock. So it's your stress, whatever you are applying, it does the two things. One is it has to overcome the friction going on between the particles. And another is it has to overcome the bond between the particle, and that bond is created due to this adhesive. It's already existing. So it has to overcome these two things. Okay. Now, so far, this is the understanding of how does the rock fail, but there may be another factor also which we do not know yet. Okay. Now, young mind like you, maybe someday you will find out, no, there is another factor is also there. Due to this also rock fails. Okay. But so far in majority of the textbooks and this thing, this is what is the understanding of failure of rock. Now, based on this, some mathematical concepts are also given, that how does rock fail, and can we give a equation that under this condition rock will fail. This is the value of sigma by which rock will fail. Okay. And what are the material properties that controls the failure of rock? Now, let me going to give you some aspect of that. Right now, let me tell you, there are maybe more than 20 such mathematical equations already derived based on the experiment. There is no analytical. Based on experiment, people understood and they have given an equation. Now, one of the most important equation is called Coulomb equation. I will put a more before just after this. It's a Coulomb's equation or Coulomb's criteria we call. Okay. Now the Coulomb, he has given maybe this equation about 170 years ago. Okay, it's a long time ago. It's not today's equation. Now that time he was working with sand, mostly sand and soil type of thing. Not soil, sand mostly. And he said that let me draw it here. That even if I apply this sigma 1 and this is sigma 3, and if it fails something like this, he said there is a shear stress act here and normal stress act here. Now, if I tell you how he has derived this, you'll say, oh, it's a very easy. Basically, if this is, you consider an element, so he has said the another element is he just rotated it. Okay, and there is a rotation and angle. Let's say this angle we normally term here beta. So he said if this is the shear plane which has a beta angle with the x-axis or the sigma 3 axis, then he said the equation is tau is equals to sigma n tan phi. Okay. Now you know this equation. Okay. This is not a complicated equation. You already know. If I tell you if S is equals to n mu, you know this equation. Do you know this equation?
What is the value of phi here? Is it beta?
The frictional force at the limiting case is equals to, that means static frictional force is equals to mu times, mu is coefficient of static friction. I can write mu s also, into the normal force, right? This you know already. Now this equation is exactly that. This tan phi is mu s. Okay, I'm going to tell you what is phi. And you see, this is just converted into stress. Okay, this shear stress and normal stress acting in this plane, whatever is the failure plane. So he has divided by the area, and that is what he said. Now here, only difference is when you do this frictional force. Let me draw it. I think this you already know. I think this kind of problem you have solved, right? If this is theta, if this is W, so this is W cos theta, this is W sin theta, and this is our frictional force, right? So can you tell me what is mu here in this problem? What is mu s?
Tan theta.
Mu s is equals to
Tan theta.
tan theta. Okay. Now what is mu s? If I write with the angle, something like tan phi, frictional angle. If I write with respect to the frictional angle, in this case, the frictional angle is the resultant force with, I think, the normal. That is the angle. Resultant force acting here with the normal force like this, and some resultant force acting here, and that is basically phi. So in this simple problem, the phi must be equals to theta, and that is the limiting case. Now here also the same. See, the equation is same, but meaning is little different. Now what is phi? Now phi is not this surface friction. Remember that this is a friction of this surface. This is the friction angle of this surface. That is what is phi. Now this is not the friction of this surface, because this surface is just how it is a path by which it has failed. Here, the Coulombs I explained that all these particles which has acted, okay, in friction while it was failing, and along that path, whatever is the combine of those frictional forces, that is basically giving us the tau, or the resisting. That is what is resisting. So opposite to that tau. Okay, like here the W sine theta is the tau and F is the friction. So here tau is W sine theta and friction is acting in the opposite direction. And that is all those internal particles, those friction forces acting along this line or along this path, is that frictional force, the combination of everything. That's why this phi is called the angle of internal friction. Remember that. It is not just a surface friction. This is called angle of internal friction. Okay. What is there? Okay. So it is coming from within the rock. It is not a surface. Okay. But equation wise, they are exactly the same. So this is what Coulomb has said. Okay. And now if I ask you, can you measure this sigma n? Because if I need to know tau, or if I need to know phi,
Yes, sir.
if that is I have to calculate, what is this tau and sigma n? How do I measure it?
So stress transformation.
Stress transformation, correct. So equation just like giving like this, tau equals to sigma and tan phi doesn't excite me at all, because I cannot measure tau and sigma n. Why? Because I do not know at which path it is going to fail, because that is coming from internal. Different rock breaks in different path. Different rocks breaks in multiple path. So there is no way I can know in which path it is going to fail. So we have to do the trace transformation. What we know here sigma 1 and sigma 3. So we have to convert it into sigma 1 and sigma 3, because at which sigma 1 it has failed I already know, and sigma 3 is the applied, how much I have applied all through the experiment, how much stress I have applied or how much confinement pressure I have applied. So this sigma 3 is known to me. Sigma 1 also known to me after the rock has failed. That is the maximum value. Okay. So I have to do the stress transformation. I'll do that next week, not today. Now you are saying, sir, आप तो बोला है कि there is a bond. Where is that bond? Friction. Now you understood that what friction it has to overcome. But where is that bond? While working with rock, it was realized that this equation doesn't work. But it works only for sand, okay, but not for rock. Rock has a binding material. Then this equation was modified something called C. It's a constant, sigma and tan phi. Now C is called cohesion. Cohesion, adhesion, it is basically the same thing. So in other words, if I have to draw it to you, if I now plot in sigma n tau plane, so this is the Coulomb criteria. This is my phi. So this line is tau equals to sigma n tan phi. And the next line which I have given, this is basically C. There is an intercept. And this is tau is equals to C plus sigma n tan phi. Now there are this has two parameters, C and phi, two properties. One is cohesion, another is friction angle, and this one is single parameter. What it is saying is that there is a residual type of strength, which is the bond strength, even it has sigma n equals to 0. Okay, so firstly, I have to overcome that C, otherwise nothing will happen. Okay, I have to overcome that C, the cohesion. So there are two parameters we need to find out, this C and phi, from these experiments, and these are the material properties of the rock. We have to find that out. The cohesion and friction angle of any rock, we should be able to find out. And once we know this, then only we can establish this equation. Then it becomes tau equals to C, whatever the value, plus sigma and tan phi, what, let's say it is 30 degree or 40 degree. So I can say this rock will fail like this. So any stress here, is it fail or safe? If my sigma n is here and sigma tau is here, is it fail or safe? This much is sigma n and this much is tau. Is it safe or fail? And if a point is here, fail or safe? The green one and blue one. Can anybody tell me for this graph? Not this one, for that one. The blue one is safe or fail? If this is the value, you understand the question, right?
I
Let's
think
say your
safe.
friend is which one is safe?
Blue one.
Blue one or green one?
Blue one.
Blue one is safe. Why?
Because it is less than tau, so basically it is the maximum that can apply is
Yeah,
along
right.
the line.
So exactly right. Okay. And green one is fail. So this curve or this line is called MC envelope. More Coulomb. I will tell you why the more comes in the next class. But this is now a famous more Coulomb criteria, or we call it envelope. Why envelope? Because below this is everything safe. That means elastic. And above this is fail. Okay. This is fail. Okay. This one is fail. This side is fail and this side is safe. So this line is dividing the failure and safe zone. Okay, that's why we need to know C and phi. Now you can see this may be like this may be like that. So it may be a different line based on the intercept C and the friction angle phi. Okay, so this is a simple straight line in tau sigma and plane, and where tan phi is the slope and C is the intercept. Okay, so today you know this much. So next class I'm going to derive it by changing the uh, by transforming the stress from C. So I will bring it to sigma 1, sigma 3 plane, and then you will better understand how its shape and what it means. Okay. So I stop here.